Thank you for listening to the Sleepy Mind channel. Redwood trees are the tallest living trees on Earth, rising higher than any other plant that has ever grown on land. Their height is not an exaggeration of scale, but a measurable physical reality, with some individuals extending well beyond 300 feet, placing their upper branches higher than many city buildings. These trees exist today in a narrow stretch of the world, shaped by specific coastal conditions instead of broad adaptability. And if you like stories like these, please like and subscribe. Redwood trees belong to a landscape where height, moisture, and time work together slowly. Their presence is not scattered or accidental. It's the result of stable coastal environments that allow steady growth to continue for centuries without interruption. Let's begin. Redwood trees are defined first by their physical size. They are not simply tall in comparison to nearby trees, but taller than any other species that has ever reached maturity on Earth. This height is built gradually, layer by layer, through continuous upward growth that doesn't stop once the tree reaches adulthood. A mature redwood doesn't reach a final height and settle into maintenance. It continues to extend upward as long as conditions allow, adding new height year after year. The tallest known redwood exceeds 380 feet. At that height, the tree's crown exists in a different physical environment than its base. Wind, light, and moisture behave differently near the top than they do near the forest floor. The trunk connects these zones as a single continuous structure, moving water upward from the ground while supporting enormous weight above. The fact that a living organism can maintain this connection over such distance is central to what a redwood tree is. Redwoods don't grow everywhere. Their natural range is narrow and clearly defined. They grow primarily along the Pacific coast of North America, forming a long but thin band that follows the shoreline instead of spreading inland. This distribution reflects their dependence on coastal conditions instead of temperature alone. The ocean plays a direct role in shaping the environment that allows redwoods to exist. Along this coast, the climate remains relatively cool throughout the year. Extreme heat is rare, and temperatures change gradually instead of abruptly. These conditions reduce stress on long-lived trees that rely on steady biological processes. Rapid temperature swings would interfere with growth and water movement within the trunk. The coastal climate instead supports continuity, allowing redwoods to function without frequent interruption. Fog is a defining feature of the redwood environment. During dry summer months, rainfall becomes scarce, yet redwoods continue to receive moisture through coastal fog that drifts inland from the ocean. This fog forms when warm air meets cooler ocean currents, creating dense layers of moisture that move through the forest canopy. The fog is not an occasional event. It's a recurring presence that shapes the daily conditions in which redwoods live. Redwood trees interact directly with this fog. Moisture settles on their needles and branches, collecting as droplets that eventually fall to the ground. This process, often called fog drip, supplements rainfall and maintains soil moisture during periods when precipitation is otherwise limited. Without this additional water source, the coastal summer climate would be too dry to support continuous growth at such scale. The leaves of redwood trees are capable of absorbing water directly from fog. Moisture taken in through the canopy contributes to hydration at the upper levels of the tree, reducing strain on the water transport system within the trunk. This ability becomes increasingly important as height increases, because moving water vertically over hundreds of feet requires constant pressure and uninterrupted flow. The forest floor beneath redwoods reflects this steady input of moisture. Soils remain damp for much of the year, even when rain is absent. The gradual dripping of water from needles and branches distributes moisture evenly instead of in sudden bursts. This creates a stable environment where the ground doesn't dry out quickly, supporting long-term root systems and slow nutrient cycling. Redwoods are evergreen trees. The needles themselves are flat and relatively soft. Their shape increases surface area, helping capture moisture from fog, while also allowing efficient light absorption in shaded environments. The softness of the needles reflects their function instead of fragility. They are designed to persist in damp air, resisting damage from constant moisture while remaining flexible in coastal winds. Redwood trees grow faster than many other long-lived tree species. This growth doesn't occur in short bursts, but as steady annual addition. Even as young trees, redwoods establish height quickly, allowing them to reach light above surrounding vegetation. As they mature, growth continues at a slower but persistent pace, adding height and mass over centuries instead of decades. Their ability to grow quickly and live for long periods is not common among trees. Many species either grow rapidly and die young, or grow slowly and live long. Redwoods combine both traits. A redwood is not only defined by how tall it can get, but by the narrow coastal strip where that height is possible. Cool air, frequent fog, and steady seasons support the kind of slow, uninterrupted growth that can keep adding height for centuries. The redwood forest is not just a collection of tall trees. In a mature grove, the canopy holds moisture, the air stays cooler, and growth continues in small yearly additions that stack up over centuries. A redwood tree stands as a single organism, but it's also a record of place. Its size tells the story of moisture arriving when needed, temperatures remaining within a narrow range, and disturbances occurring infrequently enough to allow uninterrupted growth. The tree doesn't adapt quickly to change. Instead, it persists where change arrives slowly. The redwood tree is defined by physical presence and geographic restraint at the same time. It reaches higher than any other tree, yet it exists only where conditions allow that height to be supported year after year. Its form follows its location. The tallest trees on Earth grow where stability lasts long enough for height to accumulate. Redwood trees belong to a very specific biological identity. They are conifers, meaning they produce cones instead of flowers, and they carry their leaves as needles instead of broad blades. Within this broad group, redwoods are part of a small lineage that has changed very little in. The species commonly referred to as the coastal redwood is defined by its evergreen nature. The tree doesn't shed its needles seasonally. Instead, individual needles persist for several years before being replaced gradually. This allows the tree to maintain a continuous photosynthetic surface, which is essential for supporting both height growth and long lifespan. Energy intake doesn't pause for a dormant season. It continues whenever light and moisture are available. The needles themselves are arranged along the branches in a flattened pattern. In younger trees and lower branches, the needles spread outward, maximizing surface area. In higher branches exposed to wind and stronger light, the needles become shorter and more compact. This variation within a single tree reflects adaptation to different physical conditions at different heights. Redwood needles are soft to the touch, compared to many other conifers. They don't contain sharp points or stiff edges. This softness is not incidental. It reflects a balance between durability and flexibility. The needles must withstand constant moisture from fog while bending instead of breaking in coastal winds. Their texture allows water to cling briefly before dripping downward, contributing to moisture transfer within the forest. As evergreen conifers, redwoods rely on cones for reproduction. Both male and female cones are produced on the same tree. Male cones release pollen into the air, while female cones receive it and develop seeds. The cones themselves are relatively small compared to the size of the tree. This contrast between massive structure and delicate reproductive organs is a defining feature of the species. Redwood seeds are extremely small. Each cone contains many seeds, yet the vast majority never grow into mature trees. Their size allows them to be carried short distances by wind, but it also makes them vulnerable to drying, burial, or competition. Successful germination requires a narrow combination of moisture, light, and exposed soil. This low success rate is offset by longevity and alternative regeneration methods instead of sheer reproductive volume. Beyond seed reproduction, redwoods possess the ability to regenerate vegetatively. New shoots can sprout directly from the base of an existing tree or from the root system of a fallen trunk. These sprouts are genetically identical to the parent tree. This trait allows redwood individuals to persist even after damage or partial destruction. It also means that a single genetic individual can exist as a cluster of trunks instead of a solitary stem. That capacity for basal sprouting is unusual among large conifers. It contributes significantly to the resilience of redwood groves. When a mature trunk is damaged by fire, wind, or cutting, new growth can emerge without the need for seed germination. The energy stored in the root system supports this regrowth, allowing recovery to begin quickly once conditions stabilize. Redwood bark is another defining trait. It's exceptionally thick, often exceeding a foot in depth on mature trees. The bark is fibrous instead of rigid, composed of layered tissue that cushions the living core of the tree. This thickness serves multiple functions, but its most important role is protection. It insulates the inner tissues from heat, physical damage, and biological threats. Unlike many conifers, redwood bark contains very little resin. Resin is a flammable substance that can increase fire intensity. By limiting resin content, redwoods reduce the likelihood that their bark will ignite easily. Instead of burning, the outer layers may char, while the inner tissues remain intact. This trait allows mature trees to survive fires that would kill less protected species. The wood of redwood trees contains high levels of tannins. These chemical compounds deter insects and slow the growth of fungi and bacteria. Internally, the structure of redwood wood supports both height and flexibility. The trunk must be strong enough to support enormous vertical weight, while remaining flexible enough to sway without snapping. This balance is achieved through wood fibers that distribute stress gradually instead of concentrating it at single points. Movement in wind becomes a form of protection instead of a threat. Redwood roots differ from what might be expected given the tree's height. They don't extend deep into the ground as a single taproot. Instead, they spread outward in a wide, shallow network. Individual roots interlock with those of neighboring trees, creating a shared support system. Stability emerges from connection instead of depth. That interwoven root structure means that redwoods often grow in groves instead of as isolated individuals. Each tree contributes to the identity of a redwood tree extends beyond a single trunk. Needles capture fog moisture, bark resists fire heat, wood resists decay, and shallow roots spread wide and interlock with neighbors. Together, these features support long life and steady growth in a narrow coastal climate. Classification alone doesn't fully describe what makes a redwood distinct. Its defining traits operate together over long periods. Evergreen needles allow continuous energy intake. Thick bark protects accumulated growth. Shallow, interlocking roots stabilize massive structures. Chemical defenses slow decay and damage. Regenerative sprouting ensures continuity even after disruption. Because the bark is thick, the wood resists decay, and the roots interlock, a redwood can keep standing and growing for centuries. The tree is built to endure in places where conditions stay relatively stable and where fires and storms come and go without removing the whole forest. Redwood trees begin their existence in ways that contrast sharply with their eventual size. The earliest stage of a redwood's life is defined by fragility instead of strength. From cones, no larger than a small walnut, seeds are released that are among the smallest produced by any large tree. Each seed contains only a minimal reserve of energy, enough to begin growth, but not enough to survive prolonged hardship. When seeds are released, most don't succeed. They fall onto forest floors already occupied by thick layers of organic material, fallen needles, and competing plants. Many dry out before moisture becomes available. Others are shaded too heavily to begin photosynthesis. Some are buried too deeply to reach the surface. Successful germination depends on a narrow set of conditions arriving at the same time. For a redwood seed to establish, exposed mineral soil is often required. This soil may appear after fire clears surface debris or when a fallen tree disturbs the forest floor. Light must reach the ground, but not in excess. Moisture must be present consistently, but without saturation that would rot the seedling. These conditions don't occur frequently, which explains why seed-based regeneration is rare, despite the number of seeds produced. When a seed does germinate successfully, early growth is slow and cautious. The seedling produces a thin stem and a small set of needles that begin capturing light immediately. At this stage, the plant is highly vulnerable. Small changes in moisture or temperature can halt growth or cause death. Many seedlings survive only a short time before conditions shift. The early development of a redwood is shaped less by competition and more by survival through stability. Growth continues only when environmental conditions remain steady for extended periods. If moisture arrives regularly and light remains filtered instead of intense, the seedling can persist long enough to establish a root system. Once roots spread outward and anchor into surrounding soil, the young tree becomes more resilient. As growth continues, the young redwood begins to prioritize height. Even in early stages, redwoods show a tendency to grow vertically instead of branching outward. This pattern reflects the long-term strategy of the species. Height is accumulated gradually, but direction is established early. Over decades, a young tree transitions from vulnerability to persistence. Bark thickens slowly. The trunk widens as layers of wood are added each year. Needles become more numerous, increasing energy intake. At this stage, the tree is still small, relative to its eventual form, but the foundation has been laid for long-term growth. Not all redwoods begin life from seed. An equally important pathway involves sprouting from existing trees. When a mature redwood is damaged or cut, new shoots can emerge from the base of the trunk or from the root system. These sprouts draw on stored energy, instead of relying on seed reserves. Sprout-based growth allows redwoods to recover after disturbance. Fire, for instance, may damage or kill a trunk without destroying the root system. In such cases, multiple new stems can emerge from the same base. These stems grow close together, forming what appears to be a cluster of trees. In reality, they may all belong to the same genetic individual. That method of regeneration means that some redwood individuals persist through repeated cycles of damage and regrowth. A single genetic line can continue for centuries, even as individual trunks rise and fall. Early development in these cases is not about establishment from scratch, but about rebuilding structure using existing foundations. As young redwoods grow, they often do so in proximity to others. Groves form not by chance, but through shared environmental conditions and interconnected root systems. Early in development, roots spread outward instead of downward. As neighboring trees do the same, roots encounter one another and interlock. This creates mutual support even while trees are still relatively small. The early formation of groves influences growth patterns. Trees supported by shared root networks are less likely to topple in wind. Stability allows uninterrupted upward growth. Over time, this cooperative structure contributes to the extraordinary heights redwoods can achieve. Early development is not an isolated process, but one shaped by collective presence. The age of redwoods reflects the success of these early stages. Some living individuals began growing more than 2,000 years ago. These trees survived because their early development occurred during long periods of environmental stability. Once established, they continued growing through centuries marked by gradual change instead of abrupt disruption. Determining the exact age of redwoods can be difficult. Growth rings are often irregular due to variable growth conditions and internal wood structure. Fires, injuries, and periods of slow growth can obscure annual patterns. Even so, the great age of many redwoods is clear from their size and historical context. The earliest stages of redwood development occurred long before modern human influence on the landscape. These trees began growing when climates were shaped by natural cycles instead of industrial change. Their survival into the present reflects not adaptability to rapid shifts, but persistence through long spans of relative consistency. As redwoods mature from early development into long-term growth, they continue adding height instead of closing off growth at a set size. There's no genetically fixed height limit that stops upward expansion. As long as conditions allow water transport and structural support, growth continues. This principle is established early and maintained throughout life. Early development also sets the pace of growth. Redwoods don't rush through juvenile stages. They grow steadily, responding to available resources instead of forcing expansion. This measured pace reduces stress on internal systems and supports longevity. Each year adds a small amount of structure, and those additions accumulate without weakening the whole. By the time a redwood reaches maturity, its early history remains embedded in its form. The direction of growth, the spacing of branches, and the structure of roots all reflect conditions present during establishment. Early development determines how the tree will interact with its environment for centuries to come. A redwood begins from seed or from sprout during a narrow window when light and moisture line up. Most seedlings fail, but the few that establish can keep adding height and wood year after year, as long as the coastal conditions remain steady. Redwood trees are defined by longevity in a way that few living organisms can match. Once established, They persist not for decades, but for centuries, and in many cases, for more than 2,000 years. This long lifespan is not the result of dormancy or slow replacement of tissues alone. It comes from continuous function. The tree remains active, growing and responding to its environment throughout its life, instead of entering a prolonged decline. Some living redwoods began growing before the Roman Empire. Their earliest years unfolded in landscapes shaped entirely by natural forces. Over the centuries that followed, they experienced gradual shifts in climate, recurring fires, and changing ecosystems around them, yet they remained rooted in place. Their continued survival reflects an ability to maintain internal stability, even as external conditions fluctuate slowly. Longevity in redwoods is supported by the way growth continues over time. Unlike many trees that reach a mature height and then focus primarily on maintenance, redwoods continue to grow taller for centuries. There's no genetically fixed height limit that signals the end of vertical growth. As long as water can be transported upward and structural integrity can be maintained, the tree adds height incrementally. That ongoing growth means that age doesn't bring stagnation. Even very old redwoods continue producing new wood, new needles, and new roots. The tree doesn't become static. Instead, it remains engaged in the same biological processes that supported its early development, simply extended over a much longer timeline. Determining the precise age of a redwood can be difficult. Growth rings are not always clear or evenly spaced. Periods of slow growth, fire damage, or internal decay can disrupt the formation of distinct annual rings. In some cases, rings may merge or become compressed, making counting unreliable. Despite this, the great age of many individuals is evident from their size and historical records of surrounding landscapes. Longevity is also supported by the tree's resistance to decay. The wood of redwoods contains high levels of tannins, which slow the activity of fungi and insects that would otherwise break down living tissue. This chemical protection reduces internal damage over time, allowing structural components to remain functional far longer than in many other species. The bark plays a critical role in long-term survival. Its thickness insulates the living inner layers from physical injury and heat. When fires pass through a redwood forest, flames may scorch the outer bark, but the core tissues often remain unharmed. This allows the tree to continue functioning after events that would kill less protected species. Fire doesn't interrupt longevity in redwoods in the way it does for many trees. Instead, it often clears surrounding vegetation, reducing competition for light and resources. Mature redwoods are adapted to survive repeated natural fires, and these events become part of the long-term rhythm of the forest instead of a threat to persistence. The shallow but widespread root system also contributes to longevity. Roots interlock with those of neighboring trees, providing collective stability. This reduces the likelihood of toppling in storms, even as the tree grows taller and heavier. Stability gained through connection allows the tree to remain upright over centuries of exposure to wind and weather. Longevity in redwoods is not only about avoiding death, it's also about maintaining functional systems over long periods. Water transport from roots to canopy must remain efficient despite increasing height. Structural fibers must continue distributing stress evenly as mass increases. Energy production through photosynthesis must keep pace with the demands of growth and repair. The tree manages all of this continuously instead of cycling through periods of decline and renewal. As redwoods age, they don't reduce their rate of carbon intake in the way many trees do. Old-growth redwoods continue capturing and storing carbon throughout their lives. This ongoing accumulation reflects active growth instead of passive existence. Age doesn't diminish their role as functioning biological systems. Longevity also emerges from the ability to recover from damage. When sections of a tree are injured or lost, growth can adjust around the affected area. New wood forms to compensate for structural changes. Sprouting from the base or roots can replace lost trunks without ending the life of the genetic individual. This capacity for recovery allows redwoods to persist through disturbances that would end the lifespan of other trees. Over centuries, fallen redwood trunks become part of the forest floor. These logs decay slowly, sometimes persisting for hundreds of years. While no longer alive, they continue influencing the environment by storing carbon and providing habitat. The long persistence of fallen wood mirrors the longevity of standing trees, extending the influence of each individual beyond its living phase. The passage of time within a redwood forest is layered. Living trees reflect centuries of growth. Fallen logs reflect centuries of slow decay. Together, they create a landscape where processes unfold over extended timescales. Longevity is expressed not just in individual lifespans, but in the continuity of the forest as a whole. Redwoods have survived ice ages and long-term climate shifts because those changes occurred gradually. Their biology is suited to environments where stability dominates over rapid transformation. Longevity is supported when change arrives slowly enough for internal systems to adjust without being overwhelmed. The persistence of redwoods into the present depends on the same principles that supported their long past. Continued stability, protection from extreme disturbance, and preservation of the coastal conditions they require allow these trees to keep functioning across centuries. Longevity is not guaranteed. It's maintained through the alignment of biology and environment over time. The age of a redwood is not just a number of years. It represents a continuous chain of successful functioning. Each year added another layer of wood, another season of needles, another cycle of water movement and energy capture. Longevity emerges from the accumulation of these uninterrupted processes instead of from any single adaptation. Standing today, an ancient redwood embodies thousands of years of persistence. Its form reflects every season it has endured. The tree doesn't carry memory, but its structure records the conditions that allowed it to remain alive. Longevity in redwoods is the visible outcome of sustained growth under stable conditions, extended across time spans that exceed human lifetimes many times over. Redwood trees survive only within a narrow set of environmental conditions. Their continued growth depends on a specific balance of temperature, moisture, and seasonal stability. These conditions are not broadly distributed across continents. They occur primarily along the Pacific coast, where the influence of the ocean moderates extremes and creates a predictable rhythm across the year. Temperature is one of the most important constraints. Redwoods grow best where temperatures remain cool to mild instead of hot or cold. Prolonged heat places stress on internal water transport systems, while extended freezing damages living tissues. Coastal regions reduce both risks. The ocean absorbs and releases heat slowly, preventing sharp seasonal swings that would disrupt growth. Moisture availability is equally critical. Redwoods require consistent access to water throughout the year. Rainfall alone is not sufficient in their range, particularly during summer months when precipitation declines. The survival of redwoods depends on the presence of coastal fog that forms regularly and moves inland through forested valleys. Fog arrives when warm air meets cooler ocean currents, creating layers of suspended moisture. These layers drift into redwood forests during evenings and mornings, bathing the canopy in fine droplets. This process supplements rainfall and extends the growing season beyond what precipitation alone would allow. Without fog, summer conditions would be too dry to support sustained growth. Redwoods interact actively with this moisture. Needles capture fog droplets, which collect and fall gradually to the ground. This steady drip maintains soil moisture during periods when rain is absent. The process also reduces evaporation by shading the forest floor and cooling the air beneath the canopy. Some moisture is absorbed directly through the leaves. This reduces the demand placed on roots to pull water upward through the trunk. As trees grow taller, transporting water from soil to canopy becomes increasingly challenging. Foliar absorption helps balance this system, particularly in the upper reaches of very tall trees. Soil conditions must also align with these moisture patterns. Redwoods grow best in soils that drain well, while retaining enough organic matter to hold water. Prolonged saturation deprives roots of oxygen, while rapid drainage leaves soil too dry between fog events. The soils beneath redwood forests strike a balance shaped by slow nutrient cycling and steady moisture input. The forest itself modifies local conditions. Dense canopies trap moisture and reduce wind, creating a humid microclimate beneath the trees. Temperatures under redwoods remain cooler during the day and warmer at night compared to open areas. This moderation reduces stress on both roots and foliage, supporting continuous growth. Light availability is another factor shaped by environment. Redwoods tolerate shade well, especially in early stages. Filtered light passing through fog and canopy allows photosynthesis without overheating or excessive water loss. Direct, intense sunlight combined with dry air would increase evaporation and strain internal systems. Seasonal patterns matter as much as averages. Redwoods rely on predictability instead of abundance. Rain arrives primarily in winter. Fog supplements moisture in summer, and temperatures remain within a narrow range year after year. This consistency allows biological processes to operate without frequent interruption. Prolonged drought disrupts this balance. When fog patterns weaken or rainfall declines for extended periods, even mature redwoods experience stress. Water transport slows. Growth eases back. In severe cases, upper branches may die back due to insufficient hydration. Recovery depends on the return of stable moisture instead of short-term rainfall. Climate change poses a particular challenge because it threatens the fog patterns redwoods rely on. Changes in ocean temperature and atmospheric circulation can reduce fog frequency or alter its timing. Even small shifts can have large effects on forests adapted to narrow margins. Reduced fog places pressure on systems that evolved to depend on it. Because of this sensitivity, redwoods function as indicators of environmental change. Their growth responds to subtle shifts in moisture and temperature over time. Declines in growth rates or changes in canopy health often reflect broader changes in regional climate instead of isolated events. Redwoods don't migrate quickly. Their long lifespans and slow reproductive success mean they can't easily relocate in response to changing conditions. Survival depends on the continued presence of suitable environments where they already exist. This makes protection of existing forests especially important. Environmental requirements extend beyond individual trees. The surrounding forest community contributes to stability. Ferns, mosses, and shrubs retain moisture and protect soil. Fallen logs slow runoff and store water. Together, these elements reinforce the conditions redwoods need to survive. The narrow climate range that supports redwoods explains both their grandeur and their vulnerability. They achieve extraordinary size where conditions remain steady for centuries. When that stability is disrupted, growth falters instead of adapts rapidly. Survival depends on continuity instead of flexibility. Redwoods persist where moisture arrives gently, temperatures remain moderated, and seasons follow predictable patterns. Their environmental needs are not extreme, but they are precise. The trees endure not because they tolerate everything, but because they exist where little changes too quickly. Redwood trees are built from materials that support extreme height while remaining functional over centuries. Their physical structure reflects a balance between strength, flexibility, and protection. Every visible layer of the tree contributes to maintaining stability as mass increases year after year. The most immediately noticeable structural feature of a redwood is its trunk. The trunk grows straight and vertical, widening gradually from top to base. This taper distributes weight efficiently, allowing the tree to support enormous mass without concentrating stress at any single point. The trunk doesn't rely on rigidity alone. It's designed to flex under pressure instead of resist it completely. Inside the trunk, wood fibers are arranged to manage both compression and tension. As wind moves through the canopy, the trunk bends slightly, absorbing force and releasing it gradually. This movement prevents snapping and reduces fatigue over time. Flexibility is essential at great heights, where wind speeds increase and forces become stronger. The wood itself is relatively lightweight for its volume. This reduces Surrounding the wood is the bark, which is among the thickest of any tree species. On mature redwoods, bark can exceed a foot in thickness. It's composed of fibrous layers instead of solid plates. This texture allows the bark to absorb impact and heat without transmitting damage inward. The bark contains very little resin. In many conifers, resin increases flammability. In redwoods, low resin content reduces the likelihood of ignition. When fire passes through a redwood forest, the bark may char on the surface while insulating the living tissues beneath. This protection allows the tree to survive repeated fires without losing structural integrity. Bark thickness also protects against physical injury. Falling branches, shifting debris, and minor impacts don't easily penetrate to the living core. Over centuries, this resistance to damage preserves the continuity of growth. Injuries that would weaken other trees become superficial instead of fatal. The outer surface of the bark is often deeply furrowed. These grooves increase surface area and help dissipate heat. They also allow moisture from fog and rain to move downward slowly instead of running off immediately. The bark participates in moisture management as well as protection. Above the trunk, branches extend outward in layered tiers. Lower branches are longer and spread wider, while upper branches are shorter and more compact. This arrangement balances light capture with structural support. Weight is distributed closer to the trunk as height increases, reducing leverage that could cause breakage. Branches are flexible instead of brittle, They bend under wind load, reducing stress at attachment points. When branches do break, the tree's size and redundancy allow it to continue functioning without major loss. Structural failure in one area doesn't compromise the entire system. The needles are attached along these branches in patterns that maximize exposure while minimizing damage. Flat, soft needles reduce wind resistance and prevent tearing. Their shape also supports moisture capture without adding excessive weight. The cumulative mass of foliage is large, but it's distributed across thousands of small, lightweight units. Below ground, the root system provides anchoring instead of deep penetration. Redwood roots spread outward in a wide, shallow network. This structure reflects the moist soils of coastal environments, where deep taproots are less effective than broad support. Roots interlock with those of neighboring trees. This interconnection creates a shared structural base. Individual trees are stabilized by the presence of others, reducing the likelihood of uprooting during storms. The forest becomes a cooperative structure instead of a collection of isolated supports. The shallow nature of the roots allows access to oxygen-rich upper soil layers. In consistently moist environments, deeper soils may lack sufficient oxygen. By spreading laterally, roots maintain efficient respiration while absorbing water and nutrients distributed across the forest floor. Structural stability emerges from this combination of wide root networks and flexible trunks. The tree doesn't rely on any single component to maintain balance. Instead, forces are distributed across bark, wood, branches, and roots. Each part contributes incrementally to the whole. As redwoods age, their structure adapts without losing coherence. Additional layers of wood thicken the trunk. Bark continues to build outward. Roots expand further into surrounding soil. The tree grows larger, but the same principles apply at every scale. Physical structure also supports longevity. Resistance to decay, fire, and mechanical stress reduces the accumulation of damage over time. The tree remains structurally sound, even as individual components weather and renew. This continuity allows growth to proceed without interruption. The materials that make up a redwood are not extraordinary in isolation. Wood, bark, roots, and needles exist in many trees. What sets redwoods apart is how these materials are arranged and maintained over time. Structure is not optimized for speed or efficiency alone, but for endurance. Every aspect of the redwood's physical form serves the same outcome. Height is achieved without sacrificing stability. Protection is maintained without halting growth. Flexibility replaces rigidity where movement is unavoidable. Connection replaces isolation where support is required. The redwood stands because its structure allows it to remain standing. Over centuries, storms pass, fires burn, and growth continues. The tree doesn't resist these forces aggressively. It accommodates them, distributing stress and preserving function. That physical design explains how redwoods maintain integrity as they grow larger than any other trees. Their materials are arranged to support persistence instead of perfection. Structure evolves gradually, reinforcing itself year after year, allowing the tree to remain upright and alive across spans of time that far exceed a human life. Redwood trees follow growth patterns that emphasize persistence instead of speed. From early stages through maturity, growth occurs steadily, guided by available resources instead of fixed schedules. The process is continuous, unfolding year after year without a defined endpoint. Height growth begins early, Even young redwoods show a tendency to prioritize vertical extension over wide branching. This upward focus allows access to light above surrounding vegetation. As the tree grows taller, each year adds a thin layer of new wood to the trunk, increasing both height and diameter. Growth is incremental instead of dramatic, but it doesn't stop once maturity is reached. Redwoods grow faster than many other long-lived trees during early and middle stages of life. Once they reach the upper canopy, growth slows slightly, but remains consistent. The tree doesn't enter a terminal phase where height growth ceases. Instead, it continues adding height for centuries as long as conditions remain favorable. The absence of a genetically fixed height limit is central to this pattern. Growth is constrained by physics and environment instead of by internal programming. As long as water can be transported to the top of the tree and structural support remains intact, vertical growth continues. When growth slows, it reflects external limits instead of age alone. Diameter growth accompanies height increase. Each year, a new layer of wood forms beneath the bark. This thickening strengthens the trunk, allowing it to support additional mass above. The relationship between height and width remains balanced. As the tree grows taller, it also grows stronger, maintaining stability over time. Branch formation follows a layered pattern. Lower branches form early and may persist for long periods if light remains available. As the canopy rises, lower branches may lose access to light and eventually fall away. This natural pruning directs energy upward and reduces unnecessary weight lower on the trunk. Upper branches remain active and continue forming new foliage. These branches are shorter and more compact, reducing leverage and wind resistance. Growth in the crown adjusts continuously to light availability and wind exposure. Branches expand where conditions allow and remain limited where stress is higher. Needle production is ongoing. Needles are replaced gradually instead of all at once. Older needles fall as new ones form, maintaining a stable photosynthetic surface. This steady turnover supports continuous energy intake without sudden drops in capacity. Growth also occurs below ground. Roots extend outward each year, exploring new soil and reinforcing connections with neighboring trees. Root expansion mirrors above-ground growth, maintaining balance between support and mass. As trunks widen and crowns expand, roots spread further to stabilize the increasing load. Interlocking roots influence growth direction. Trees supported by strong root networks are less likely to tilt or lean. Upright growth remains stable, allowing continued height increase without structural compromise. Growth patterns reflect not only individual biology, but also the presence of nearby trees. Redwoods respond to resource availability instead of forcing growth during poor conditions. During periods of limited moisture or cooler temperatures, growth slows. When conditions improve, growth resumes without needing recovery from stress. This responsiveness reduces long-term damage and supports longevity. Growth rings record these patterns, though not always clearly. Years of favorable conditions produce wider rings, while challenging years produce narrower ones. Over centuries, this variability accumulates into massive trunks built from thousands of incremental additions instead of rapid expansion. Basal sprouting contributes to growth patterns at the forest scale. When a trunk is damaged or lost, new shoots can emerge from the base or roots. These shoots grow quickly, using established root systems. Over time, one trunk may replace another without interrupting the presence of the tree as a whole. In groves, growth becomes collective. Trees influence one another's access to light and stability. Height increases across the group instead of in isolation. This shared growth pattern reinforces dominance of the grove within the landscape. Redwoods don't rush toward a final form. Growth unfolds as a long sequence of small changes that accumulate. Each year adds slightly more height, slightly more width, and slightly more reach below ground. No single year defines the tree. Persistence does. The result of these growth patterns is scale achieved through patience. Height is not achieved quickly, but it's maintained once reached. Strength builds gradually, matching expansion at every stage. The tree remains functional throughout growth instead of growing first and stabilizing later. Growth in redwoods reflects a long-term agreement between biology and environment. As long as conditions remain supportive, growth continues. When conditions limit expansion, growth pauses instead of forcing adaptation. This restraint preserves structure and allows growth to resume later without damage. Over centuries, these patterns produce the tallest trees on Earth, not through bursts of acceleration, but through uninterrupted accumulation. Growth is steady, responsive, and persistent. The redwood grows by remaining alive and functional year after year, allowing time itself to build its form. Redwood trees follow rhythms shaped by seasonal cycles instead of fixed internal schedules. Their timing is governed by the availability of moisture, light, and temperature stability across the year. Growth doesn't occur in sharp bursts or pauses. Instead, it rises and falls gently in response to environmental signals. The primary annual cycle begins with winter. During this season, rainfall is most abundant in redwood regions. Soils become saturated but remain well drained. Roots absorb water steadily, replenishing internal reserves that will support growth in the months ahead. Cooler temperatures reduce evaporation, allowing moisture to remain available for longer periods. As winter progresses, growth within the tree continues at a reduced pace instead of stopping entirely. Redwood trees don't enter a deep dormancy. Metabolic activity slows, but water transport and tissue maintenance continue. This continuity prevents shock when conditions improve and allows growth to resume smoothly. Spring brings longer daylight and gradual warming. With increasing light, photosynthesis becomes more active. Stored water and nutrients support the formation of new wood beneath the bark. Trunks thicken slightly as new layers are added. Shoots extend, and new needles begin to form near branch tips. That period marks one of the main growth phases of the year. Height increases most noticeably during spring and early summer, when moisture is still available from winter rains and temperatures remain moderate. Growth is steady instead of rapid, avoiding strain on internal systems. As summer approaches, rainfall declines. In many regions where redwoods grow, rain becomes rare or absent for months. At this point, the seasonal rhythm shifts from reliance on precipitation to dependence on fog. Coastal fog arrives frequently, especially during nights and mornings, delivering moisture directly to the canopy. Fog influences daily timing as well as seasonal patterns. Moisture condenses on needles during cooler hours, then drips slowly to the forest floor. This regular input sustains soil moisture and supports continued water uptake by roots. Growth doesn't halt in summer, but it slows slightly, adjusting to reduced water availability. During prolonged dry periods, growth becomes conservative. The tree prioritizes maintaining existing tissues over expanding rapidly. Water transport continues, but energy is directed towards sustaining needles and supporting structural integrity instead of adding significant new height or width. Autumn brings gradual changes instead of abrupt transitions. Temperatures begin to cool, and fog patterns may persist even as rainfall slowly returns. Growth continues at a reduced pace, tapering gently instead of stopping suddenly. New wood formation slows, and the tree prepares for another winter cycle. Throughout these seasonal changes, needles are shed and replaced continuously. There's no single season of leaf drop. Older needles fall as new ones form, maintaining a stable photosynthetic surface year-round. This gradual turnover avoids sharp losses in energy intake. Reproductive timing follows similar rhythms. Cones develop over extended periods instead of within a single season. Pollination occurs when conditions support pollen movement, while seed development unfolds slowly. Seeds are released when cones mature, often during dry conditions that allow dispersal. Timing also influences interactions with fire. Natural fires historically occurred during drier parts of the year. Redwoods are adapted to this timing, with bark and internal moisture levels providing protection. Fire clears competing vegetation without interrupting the long-term growth rhythm of mature trees. Over decades, these seasonal cycles repeat with minor variation. The consistency of timing supports predictable growth patterns. When seasons follow familiar sequences, redwoods maintain steady development without stress accumulation. Disruptions to timing have noticeable effects. Extended droughts, altered fog schedules, or unusual temperature shifts can slow growth or damage tissues. Recovery depends on the restoration of familiar seasonal rhythms instead of isolated weather events. The timing of growth in redwoods reflects reliance on continuity. Each year builds upon the last through repeated cycles of moisture and light. Growth doesn't depend on rare favorable moments, but on the dependable return of seasonal conditions. Over centuries, these cycles accumulate into immense size. Each season contributes a small amount of growth. Each year reinforces structure instead of transforming it. Timing remains gentle and predictable, allowing the tree to persist without interruption. The redwood's relationship with time is cyclical instead of urgent. Growth follows the rhythm of seasons, responding patiently to changes instead of forcing expansion. Through this steady timing, the tree remains aligned with its environment, adding height and strength one season at a time. Redwood trees rely on a continuous flow of resources to sustain their size and long-term growth. Water, light, and nutrients move through the tree in coordinated ways, each placing limits on how fast and how far growth can proceed. These constraints don't halt growth, but they shape it, ensuring that expansion remains balanced with function. Water is the most critical resource. Every needle depends on a steady supply to maintain photosynthesis and internal pressure. In a tree that can exceed 300 feet in height, moving water from roots to canopy is a constant challenge. The distance alone creates resistance, and gravity places limits on how quickly water can rise. Water enters the tree through roots that absorb moisture from the upper layers of soil. From there, it moves upward through specialized tissues that transport water continuously. As height increases, this transport becomes more demanding. Pressure differences between roots and leaves must be maintained without interruption. Any prolonged shortage slows growth instead of causing immediate failure. Fog plays a direct role in easing this constraint. Moisture absorbed through needles reduces reliance on upward transport alone. This additional input helps maintain hydration in the upper canopy, where water demand is highest. By supplementing root uptake, fog reduces strain on internal systems and allows continued function at extreme heights. Light is another limiting resource. Redwood forests are dense, and lower branches often receive filtered light instead of direct sun. The tree responds by prioritizing height growth, placing foliage where light is more available. As the canopy rises, light capture becomes more efficient, supporting energy production needed for maintenance and expansion. Photosynthesis converts light into chemical energy, which fuels growth and repair. This energy must be distributed throughout the tree. Long transport distances require efficient internal movement of sugars from needles to growing tissues and roots. Growth slows when energy production falls behind demand, preventing overextension. Nutrient availability also shapes growth. Redwoods grow in soils rich in organic matter, but low in rapid nutrient turnover. Nutrients are released slowly as organic material decomposes. This slow recycling aligns with steady growth instead of rapid bursts. The tree absorbs what is available and grows at a pace that can be sustained long-term. Roots play a key role in accessing these nutrients. By spreading widely, they encounter varied soil conditions and share access through interlocking networks. This distribution reduces dependence on any single patch of soil. Constraints are spread across a larger area, supporting stability instead of rapid extraction. Carbon is both a resource and a constraint. Redwoods capture large amounts of carbon dioxide through photosynthesis and store it as wood. Unlike many trees, they continue accumulating carbon as they age. Growth doesn't slow simply because the tree is old. As long as resources allow, carbon intake and storage continue. That ongoing storage increases the mass that must be supported and maintained. Structural strength must keep pace with accumulation. Resources are allocated not only to new growth, but also to reinforcing existing tissues. The tree balances expansion with maintenance, preventing weakness from developing. Energy allocation reflects this balance. When resources are abundant, growth proceeds. When resources become limited, the tree reduces expansion instead of compromising existing structure. This restraint prevents catastrophic failure and supports longevity. Constraints also arise from space. In dense groves, neighboring trees compete for light and soil resources. Interlocking roots reduce some competition, but canopy space remains finite. Growth adjusts to available gaps instead of forcing expansion into occupied areas. At the forest level, fallen trees and decaying logs return nutrients to the soil slowly. The forest functions as a closed system where resources move gradually between living and non-living components. These constraints shape the character of redwood growth. Expansion is never unlimited, but it's sustained. The tree grows until physical or environmental limits are reached, then maintains instead of declines. Growth responds to constraints by slowing, not by failing. Over centuries, this pattern allows redwoods to become the largest trees on Earth. Resources are used efficiently and conservatively. Constraints are respected instead of challenged. The tree grows within what its environment can support, extending its life instead of exhausting its systems. Resource use in redwoods reflects a long-term strategy. Water, light, nutrients, and carbon are managed continuously. Growth follows availability, and limits guide form instead of preventing it. Through this careful balance, redwoods sustain size and function across extraordinary spans of time. As redwood trees mature, they move through long periods of transition instead of distinct stages. Maturation is not marked by a sudden shift from growth to stability. Instead, it unfolds gradually as structure, resource use, and interaction with the environment change over time. These changes reflect increasing size and complexity instead of aging in the usual sense. Early in life, growth is focused on establishment. Height increases quickly relative to size, and energy is directed toward reaching light. As the tree grows larger, priorities begin to shift. Height growth continues, but increasing attention is given to strengthening the trunk, expanding the root network, and maintaining internal systems across greater distances. One important transition involves the balance between height and diameter. As redwoods become taller, the trunk thickens more noticeably each year. This widening is not simply a byproduct of age. It's a functional adjustment that allows the tree to support additional mass above. The relationship between height and width remains coordinated, preventing instability as size increases. Crown structure also changes during maturation. In younger trees, branches may extend more freely, occupying available space. As neighboring trees grow and canopies overlap, light becomes more limited in lower areas. Branches that no longer receive sufficient light gradually decline and fall away. This process reduces energy expenditure on unproductive tissue. The loss of lower branches is gradual and uneven. It doesn't occur all at once, nor does it leave the trunk bare suddenly. Instead, branches decline individually as light conditions change over time. As redwoods mature, internal transport systems adapt to increasing scale. Water must travel farther from roots to needles, and sugars must move longer distances from canopy to growing tissues. The tree responds by maintaining continuous transport pathways instead of increasing speed. Flow remains steady, reducing the risk of interruption or damage. The transition into maturity also involves changes in how growth responds to conditions. Younger trees may show more pronounced responses to favorable years, producing wider growth rings during wet periods. Mature redwoods respond more conservatively. Growth continues steadily, even when conditions fluctuate, reflecting established systems buffered against short-term variation. Reproductive activity becomes more consistent as trees mature. Cone production increases as crown size expands. This doesn't mean that reproduction replaces growth. Both processes occur together. Energy allocation adjusts so that reproduction proceeds without compromising structural maintenance. Mature redwoods also become more integrated into their surroundings. Root systems interlock more extensively with neighboring trees, strengthening collective stability. Canopies merge, shaping the forest microclimate more strongly. The tree becomes less an individual competitor and more a component of a larger system. That integration marks a transition in how the tree influences its environment. Shade deepens beneath the canopy. Moisture retention increases. Wind is reduced near the forest floor. These changes feed back into the conditions that support continued growth and survival. As redwoods continue maturing, they begin accumulating features associated with old-growth forests. Bark becomes thicker and more deeply furrowed. Cavities may form where branches once existed. These changes don't weaken the tree. Instead, they reflect ongoing adaptation to size and age. Despite these transitions, growth doesn't stop. Mature redwoods continue adding height and mass. There's no point at which the tree shifts into decline simply because it's old. As long as resources remain available and structural integrity is maintained, maturation blends seamlessly into continued growth. The pace of change slows, but it doesn't cease. Each year adds another layer of wood, another increment of height, another extension of roots. The tree remains dynamic instead of static. Maturity is not an endpoint, but a condition of sustained function. Transitions within the tree occur gradually enough that they don't disrupt continuity. Systems adjust over decades instead of years. This slow pace prevents stress accumulation and supports longevity. Maturation strengthens instead of limits the tree's capacity to persist. Environmental transitions also shape maturation. As forests recover from disturbance, light availability changes. Mature trees adjust crown structure accordingly. Growth responds to shifting competition without sudden reorganization. The tree adapts through small adjustments instead of major restructuring. The transition from younger growth to mature forest is not a single event. It's a long sequence of adjustments that maintain balance between expansion and stability. Each adjustment reflects physical necessity instead of programmed aging. Mature redwoods represent a stage where size, structure, and environment are aligned. Growth continues within established limits. Systems operate efficiently across large scales. The tree remains capable of responding to change, but does so conservatively. That form of maturation supports endurance. By avoiding sharp transitions, redwoods reduce vulnerability. They don't enter phases of rapid decline or overextension. Instead, they remain functional across centuries, with maturity serving as a stable platform for continued existence. The tree's form at maturity reflects accumulated responses to light, water, and competition. No two mature redwoods are identical, but all follow the same underlying principles. Structure adjusts gradually, preserving balance as size increases. Maturation in redwoods reflects time instead of age. Changes occur because years pass and conditions interact, not because an internal clock demands transformation. The tree continues growing, adjusting, and functioning as long as its environment allows. Redwood trees interact continuously with the world around them. Their size, structure, and persistence shape how wind moves, how water flows, how light reaches the ground, and how other living organisms survive within the forest. These interactions are not occasional events. They are constant exchanges that define the character of redwood ecosystems. Wind is one of the most persistent external forces acting on redwoods. At great heights, wind speeds increase, and forces acting on the canopy become stronger and more variable. Redwood trees respond through flexibility instead of resistance. Trunks sway gently, and branches bend instead of breaking. This movement dissipates energy gradually, reducing strain on wood fibers and attachment points. Wind interaction also influences forest structure. As redwoods move together within groves, their interlocking root systems distribute force across multiple trees. A gust that pushes one trunk transfers stress through the shared root network, reducing the likelihood of individual failure. Stability emerges from collective interaction instead of isolated strength. Light interaction changes dramatically beneath redwood canopies. The height and density of the trees filter sunlight before it reaches the forest floor. Direct sunlight becomes diffuse, arriving as soft, scattered illumination instead of intense beams. This light environment supports plants adapted to shade, including ferns, mosses, and shrubs that thrive under low, steady light conditions. The redwood canopy also alters temperature. During the day, shade keeps air cooler beneath the trees. At night, the canopy reduces heat loss, keeping temperatures more stable. This moderation protects sensitive organisms that rely on narrow temperature ranges and reduces stress caused by daily extremes. Moisture interaction is central to redwood forests. The canopy intercepts both rainfall and fog. Water collects on needles and branches before dripping slowly to the ground. This gradual delivery reduces surface runoff and allows soil to absorb moisture efficiently. Instead of sudden saturation, followed by drying, the forest floor remains consistently damp. That interaction influences water movement beyond the forest itself. Streams near redwood forests tend to stay cooler because canopy shade limits solar heating. Cooler water holds more oxygen and supports aquatic life. Fish species, particularly those sensitive to temperature, benefit from these moderated conditions. The forest floor plays an important role in these interactions. Fallen needles, bark fragments, and decaying wood form thick layers of organic matter. These layers absorb water, slow evaporation, and release nutrients gradually. Soil beneath redwoods becomes rich and stable, supporting long-term biological activity instead of rapid cycles. Fire is another external force that interacts with redwood forests. Natural fires historically moved through these landscapes at intervals. Mature redwoods are adapted to survive such events. Thick bark insulates living tissues, and high moisture content reduces internal damage. Fire often clears smaller vegetation without killing established trees. The interaction between fire and redwoods reshapes the surrounding environment. Competing plants are removed, opening space and light without disrupting the dominant canopy. This maintains forest structure while renewing understory conditions. Fire becomes a regulating force instead of a destructive one within these systems. Redwoods also interact extensively with wildlife. Their height creates vertical habitat layers that don't exist in most forests. Birds nest high in the canopy, far above ground-based predators. These elevated nesting sites remain stable year after year, supporting long-term use by the same species. Lower levels of the forest provide shelter for small mammals. Fallen logs, root hollows, and thick ground cover offer protection from weather and predators. The persistence of large fallen redwood logs creates long-lasting habitat features instead of temporary shelters. Amphibians rely heavily on the cool, moist conditions beneath redwoods. The shaded forest floor maintains humidity that prevents dehydration. Stable temperatures support species that can't tolerate rapid environmental change. These organisms depend not on individual trees, but on the forest conditions redwoods create collectively. When redwood trees fall, interaction with the environment doesn't end. Fallen trunks decay slowly due to tannin-rich wood. These logs remain intact for centuries, becoming nurse logs that support new plant growth. Seedlings establish on decaying wood where competition is reduced and moisture remains stable. Nurse logs elevate young plants above the forest floor. This position reduces competition with established roots and protects seedlings from waterlogging. Over time, roots grow down into the soil as the log continues to decompose. The fallen tree thus supports new life long after it stops growing. Nutrient cycling in redwood forests is shaped by slow interactions. Organic matter accumulates gradually and decomposes at a measured pace. Nutrients are released slowly, aligning with the steady growth of trees and understory plants. This prevents nutrient loss through rapid runoff and supports long-term soil fertility. Redwood forests also interact with sound. Thick bark, dense foliage, and layered vegetation absorb noise instead of reflecting it. Sound waves dissipate quickly, creating quieter environments. This acoustic dampening alters how animals communicate and how movement is perceived within the forest. Human interaction with redwood forests has historically altered these natural exchanges. Logging removed large trees, disrupting canopy structure, soil stability, and moisture regulation. Where old-growth forests were cleared, temperature fluctuations increased, soil dried more quickly, and habitat complexity was reduced. In protected areas, remaining ancient stands preserve these interactions. Second-growth forests are recovering, but they lack some features of old-growth systems. Canopies are lower, fallen logs are smaller, and microclimates are less stable. Over time, these interactions may rebuild as forests mature. Redwoods influence watersheds beyond their immediate surroundings. By slowing water movement and stabilizing soil, they reduce erosion and sediment flow into streams. This benefits downstream ecosystems and maintains water quality over long periods. The interaction between redwoods and their environment is multidirectional. Trees shape conditions, and those conditions in turn support the trees. Neither exists independently. Height influences light and wind. Canopies influence moisture and temperature. Roots influence soil and stability. External forces don't act on redwoods as sudden challenges. Instead, they become part of an ongoing exchange. Wind shapes form. Fire regulates competition. Water cycles are moderated instead of controlled. Wildlife integrates into structures that persist across generations. Through these interactions, redwoods function as ecological anchors. Their presence stabilizes systems that would otherwise fluctuate more rapidly. Change still occurs, but it unfolds within boundaries shaped by the forest itself. Interaction in redwood forests is not a series of events, but a continuous state. Forces act, responses follow, and balance is maintained through scale and time. The trees don't isolate themselves from their surroundings. They shape and are shaped by them simultaneously. Redwood trees have intersected with human activity in ways that differ sharply from the natural processes that shaped them over millennia. For most of their existence, redwoods grew without large-scale human alteration. Their forests developed through slow interactions with climate, fire, soil, and time. Human presence existed nearby, but it did not restructure the forests in fundamental ways. Indigenous communities lived within and around redwood regions for thousands of years. Their interaction with redwoods was limited and selective. Fallen wood was used where it was already available. Trails passed through forests without fragmenting them. The standing trees themselves were rarely cut down, and that balance shifted in the 19th century. As settlers arrived along the Pacific coast, redwoods were encountered not as ancient organisms, but as resources. Their straight trunks, enormous size, and resistance to decay made them immediately valuable. Redwood wood could be cut into long boards that resisted insects and rot, making it desirable for buildings, bridges, and infrastructure in rapidly growing settlements. Logging expanded quickly once sawmills, railways, and mechanized tools became available. Trees that had grown for hundreds or thousands of years were felled in short periods. Entire groves were cleared systematically. The The pace of removal far exceeded the natural rates of loss caused by storms or fire. What had once been a continuous forest became fragmented landscapes within a single generation. The act of logging did more than remove trees. When a redwood fell, its extensive root system was disrupted. Soil that had been stabilized for centuries became exposed. Without canopy cover, sunlight reached the ground directly, increasing evaporation and drying surface layers. Wind moved more freely through cleared areas, altering temperature and moisture patterns almost immediately. In many logged areas, fallen trees were removed entirely instead of left to decay. This eliminated the slow nutrient recycling that redwood forests depend on. Organic matter that had accumulated over long periods was stripped away. Soils lost both moisture retention and structural stability, changing the conditions under which new trees would have to grow. Fire regimes were also altered through human intervention. Natural fires had historically moved through redwood forests at intervals, clearing understory growth without killing mature trees. With logging came active fire suppression. Fires were prevented or extinguished quickly, allowing dense undergrowth to accumulate. This changed competition for light and water and altered forest dynamics in ways that did not align with long-term redwood growth. As logging continued, the scale of loss became increasingly visible. Vast areas of old-growth forest disappeared. What remained were isolated stands surrounded by second-growth forests or developed land. The continuity that supported redwood persistence over centuries was broken into fragments. Awareness of this loss led to the creation of protected areas. Parks and reserves were established to preserve remaining ancient stands. These protections halted further large-scale logging within designated boundaries. The trees within these areas were no longer treated as timber resources, but as living systems to be maintained. Protection, however, did not reverse past change. Old-growth forests that had been cut did not return quickly. Redwood forests operate on timescales far longer than human planning cycles. A forest cleared in decades requires centuries to regain the structural complexity it once had. Protection stabilized what remained instead of restoring what was lost. In logged areas, second-growth forests began to develop. Redwoods regenerated through sprouting and seed where conditions allowed. Growth was often faster than in many other tree species, reflecting the redwood's capacity for regrowth. These new forests filled space, but they differed in important ways from old-growth stands. Second-growth forests lack the towering height and layered canopies of ancient forests. Fallen logs are smaller and fewer. Soil depth and structure reflect disturbance instead of long accumulation. Microclimates are less stable, with greater temperature variation and reduced moisture retention. These differences influence how wildlife uses the forest and how water moves through the system. Human management now plays a role in shaping these recovering forests. Instead of extracting timber, management often focuses on reducing overcrowding, protecting soil, and supporting long-term development. Thinning may be used to reduce competition among young trees. Controlled fire may be reintroduced to mimic natural processes that were previously suppressed. Human influence also extends beyond direct forest management. Roads, nearby development, and changes in land use affect redwood environments indirectly. Watersheds may be altered upstream. Fog patterns may shift due to broader climatic changes influenced by human activity. These indirect effects reach even protected forests. Visitors now move through redwood forests, Primarily as observers, trails guide movement beneath the canopy. Physical interaction is limited to presence instead of alteration. This form of interaction depends on preservation of conditions that allow redwoods to continue their long-term processes. Despite protection, redwoods remain sensitive to human-caused environmental change. Prolonged drought, altered fog frequency, and rising temperatures place stress on systems adapted to narrow ranges. Mature trees respond slowly. Decline doesn't appear immediately, but growth may slow, and vulnerability increases over time. Human interaction with redwoods operates on a mismatch of timescales. Human decisions occur quickly. Their effects unfold slowly within forests that respond over decades and centuries. Actions taken now may not show full consequences for generations. Conservation efforts recognize this mismatch. Protection is framed not as a short-term project, but as a commitment to continuity. Maintaining fog-influenced climates, intact watersheds, and stable forest structure supports the processes redwoods rely on. Human restraint becomes as important as intervention. The presence of redwoods today reflects both survival and loss. Ancient trees remain standing where protection arrived in time. Absence marks where forests were removed too quickly to recover. The landscape carries both outcomes simultaneously. Human interaction has altered redwood forests profoundly, but it has not eliminated their capacity to persist. Where conditions stabilize and disturbance is limited, growth resumes. Where disruption continues, recovery slows or fails. The trees respond not to intention, but to physical conditions. Redwoods don't adjust themselves to human schedules. They continue growing at their own pace when allowed, and they decline when stability is removed. Human interaction becomes part of their environment, influencing whether long-term processes can continue uninterrupted. The future of redwoods depends on whether human actions align with the requirements of long-lived systems. Preservation doesn't accelerate growth. It simply allows time to function as it always has. Where time is protected, redwoods continue their slow expansion, one year layered upon the next, within forests shaped by centuries instead of moments. After direct human interaction alters redwood forests, changes continue long after the activity itself has stopped. The removal of trees sets off a sequence of physical and biological adjustments that unfold over decades instead of years. These post-interaction changes shape how forests recover, how systems stabilize, and how closely future conditions resemble those that existed before disturbance. When logging ends, the most immediate change is exposure. Areas that were once shaded by tall canopies are open to direct sunlight. Soil temperatures rise during the day and cool more rapidly at night. Moisture evaporates faster from exposed ground. These shifts occur quickly, but their consequences extend far into the future. Without the shelter of mature canopies, young trees experience different growth conditions. Light is more abundant, but it's also harsher. Increased sunlight can accelerate early growth, yet it also increases water demand. Seedlings and sprouts must balance faster photosynthesis with higher risk of drying. Survival depends on whether moisture remains available through fog or soil retention. Root systems left behind after logging continue influencing the soil. Decaying roots create channels that alter drainage and aeration. These spaces can improve water movement in some areas while increasing erosion in others. The underground structure of the forest changes gradually as old roots decompose and new ones form. Fallen debris plays a significant role in post-interaction recovery. Where logging operations removed most organic material, soil recovery is slower. Where fallen branches, bark, and logs remained, moisture retention improves and nutrients return gradually. The presence or absence of this material shapes how quickly biological activity resumes. In areas where large fallen logs remain, they begin functioning as nurse logs. Even when forests have been heavily altered, these logs create microenvironments that retain moisture and provide elevated surfaces for new growth. Seedlings establish more easily on decaying wood than on compacted soil, particularly in disturbed landscapes. Second-growth redwoods often arise from basal sprouts instead of seeds. These sprouts draw on existing root systems, giving them a strong early advantage. Growth can be rapid, but it follows patterns shaped by the altered environment. Trees grow closer together, competing for light and space in ways that differ from old-growth stands. As second-growth forests develop, canopy closure begins to restore some environmental moderation. Shade increases, reducing temperature extremes and slowing evaporation. Moisture retention improves. These changes support gradual return of understory plants that require stable conditions. Despite this recovery, post-interaction forests remain structurally different for long periods. Trunks are more uniform in size. Canopies lack the vertical layering found in ancient forests. Large cavities and massive fallen logs are absent. These features take centuries to form and can't be recreated quickly. Soil recovery follows its own timeline. Organic matter accumulates slowly as leaves, needles, and wood decompose. Nutrient cycling stabilizes over decades instead of seasons. The soil beneath second-growth forests becomes richer over time, but it doesn't immediately match the depth and complexity of old-growth soils. Water movement also adjusts gradually. Streams that warmed after canopy loss may cool again as shade returns. Erosion slows as roots stabilize soil. Watersheds recover function through accumulated small changes instead of sudden improvement. Post-interaction changes are influenced by how disturbance occurred. Clear-cut areas recover differently from selectively logged ones. Forests that retain some mature trees regain complexity faster. The presence of remaining old trees provides seed sources, structural diversity, and microclimate stability that support recovery. Fire behavior also changes after human interaction. Accumulated understory growth can increase fire intensity if ignition occurs. Managed reintroduction of low-intensity fire aims to reduce this risk and restore processes that support redwood dominance. Fire becomes a tool instead of an uncontrolled threat when aligned with forest rhythms. Wildlife responses unfold alongside forest recovery. Species that depend on dense canopy may remain absent for long periods. Others that tolerate open conditions move in temporarily. As structure rebuilds, habitat availability shifts again. These transitions reflect forest development instead of direct management. Post-interaction forests exist in extended states of transition. They are neither fully disrupted nor fully restored. Each year adds small adjustments. Recovery is measured not in visible milestones, but in gradual stabilization of processes. The absence of old-growth features is especially significant. Large fallen logs that persist for centuries can't be replaced quickly. Canopy ecosystems that develop in ancient trees don't exist in young forests. These elements represent time itself instead of management outcomes. Human management influences post-interaction trajectories, but doesn't control them fully. Interventions can support recovery by reducing stress and protecting processes, but they can't accelerate centuries of accumulation. Forests resume their own pace once major disturbances cease. Post-interaction change continues even in protected areas. Recovery is ongoing instead of complete. The forest remains dynamic, shaped by the legacy of past actions and the conditions of the present. Redwood forests demonstrate that removal doesn't end influence. The absence of trees shapes environments as powerfully as their presence once did. Recovery involves re-establishing balance instead of recreating the past. As time passes, differences between disturbed and undisturbed forests become less obvious at a glance, but underlying structures still differ. True old-growth characteristics remain rare and irreplaceable within human timescales. Post-interaction change reinforces the importance of continuity. Forests respond slowly but persistently when stability is restored. Where disturbance ends, processes resume. Where disturbance continues, recovery remains incomplete. The redwood forest carries memory not through awareness, but through structure. Soil layers, trunk spacing, canopy height, and fallen wood all reflect past interaction. Each new year adds another layer to that record. Recovery doesn't erase history, it builds upon it. Redwood forests continue forward from altered states, accumulating change gradually, shaped by both what was removed and what remains. Redwood trees rely on internal chemistry that supports longevity, resistance, and continued function over long periods. These chemical characteristics are not visible at a glance, but they shape how the tree responds to injury, decay, and environmental stress. Internal composition influences how wood forms, how tissues are protected, and how the tree maintains integrity as it grows larger. One of the most significant chemical features of redwood wood is its high tannin content. Tannins are complex organic compounds produced within the tree's tissues. They serve multiple protective roles, particularly against organisms that break down wood. Fungi and insects that would normally digest cellulose and lignin encounter chemical resistance when interacting with redwood tissue. That resistance slows decay while the tree is alive. Minor injuries don't readily become sites of infection. When bark is damaged or wood is exposed, tannins limit the spread of fungi into living tissues. This containment allows the tree to continue functioning without widespread internal damage. After a tree falls, the same chemistry continues to act. Fallen redwood logs decompose slowly compared to many other tree species. Tannins inhibit microbial activity, reducing the rate at which wood breaks down. Redwood wood also contains relatively low levels of resin compared to many conifers. Resin is often used by trees as a defense against insects, but it's highly flammable. By relying more on tannins and less on resin, redwoods reduce the risk of fire damage. This chemical balance supports survival in environments where fire occurs periodically. The bark shares similar chemical properties. Its fibrous layers contain compounds that resist decay and discourage insect penetration. Combined with thickness, this chemistry creates a protective barrier that isolates the living tissues beneath from external threats. Internal chemistry also influences how redwoods manage water. Living cells maintain pressure through dissolved sugars and other compounds that regulate water movement. These solutes help maintain internal balance as water travels long distances from roots to canopy. Stable internal chemistry supports consistent transport instead of rapid fluctuations. The formation of wood itself reflects chemical processes unfolding each year. As new layers of wood form beneath the bark, cellulose fibers are produced and bound together with lignin. This lignification strengthens tissues while allowing flexibility. The ratio of these compounds influences how wood responds to stress, balancing rigidity with the ability to bend. Over time, changes in growth conditions influence chemical composition subtly. Years of faster growth may produce wood with slightly different density and fiber arrangement than years of slower growth. These variations accumulate into complex internal patterns instead of uniform structure. Chemical processes also play a role in wound response. When tissues are damaged, surrounding cells alter their chemistry, producing compounds that seal off injured areas. This compartmentalization limits the spread of decay. The tree doesn't repair damage in the way animals heal wounds. Instead, it isolates affected areas chemically and structurally. That ability to compartmentalize is crucial for long-lived trees. Over centuries, injuries are inevitable. Branches break, bark is damaged, fire scars form. Chemical responses prevent these events from compromising the entire system. Redwood chemistry also influences interactions with soil. As needles, bark, and wood fall and decompose, tannins enter the soil. These compounds slow decomposition rates and influence microbial communities. Nutrient release occurs gradually instead of rapidly, aligning with steady growth patterns. Soil beneath redwoods becomes rich in organic matter, but doesn't cycle nutrients quickly. Chemical inputs from fallen materials support slow accumulation instead of immediate availability. This stabilizes nutrient supply over long periods, reducing boom and bust cycles that could stress trees. Chemical composition affects how redwoods interact with other plants. Tannin-rich litter can inhibit rapid germination of some competing species, reducing competition near established trees. This effect is subtle and doesn't prevent all growth, but it contributes to maintaining forest structure. Within living tissues, chemical processes regulate energy storage and use. Sugars produced through photosynthesis are transported and stored in wood and roots. These reserves support growth during periods when conditions limit photosynthesis, such as extended fog or reduced light. Stored energy allows continuity instead of interruption. Chemical stability also supports resistance to insects. While no tree is immune, redwoods experience relatively low levels of infestation compared to many species. The combination of tannins, low resin content, and thick bark reduces vulnerability. Insects encounter barriers that limit both access and nutritional value. Over centuries, chemical composition changes slowly. Older wood accumulates compounds that further resist decay. The interior of massive trunks becomes chemically distinct from younger outer layers. This internal layering reflects long-term accumulation instead of rapid transformation. These chemical traits are not separate adaptations acting independently. They function together. Resistance to decay supports longevity. Reduced flammability supports survival through fire. Slow nutrient cycling supports steady growth. Each chemical feature reinforces the others. Internal chemistry also influences the acoustic and physical properties of wood. Redwood's relatively low density and fiber arrangement contribute to its ability to absorb sound. While not a primary biological function, this reflects how chemistry shapes physical characteristics. Chemical processes operate continuously instead of in cycles. They don't switch on or off with seasons. Instead, they respond gradually to conditions. This continuity aligns with the redwood's broader strategy of persistence instead of rapid response. The chemical composition of redwoods underpins every visible trait. Height depends on wood strength. Longevity depends on decay resistance. Fire survival depends on low flammability. Each outcome arises from internal chemistry, acting over long periods. These processes unfold quietly. There's no dramatic chemical event that defines a redwood's life. Instead, small adjustments accumulate year after year. Compounds are produced, stored, and redistributed. Protection is maintained through consistency instead of intensity. Internal chemistry allows redwoods to remain structurally sound and biologically active across centuries. Without these chemical defenses and balances, physical size alone would become a liability. Chemistry turns scale into stability. The redwood tree stands not only because of its shape and environment, but because of the substances that compose it. Invisible to the eye, these compounds guide how the tree resists damage, manages resources, and persists through time. As long as these chemical systems continue operating within stable conditions, the tree remains functional. Growth continues, decay is delayed, survival extends. Chemistry becomes the quiet foundation beneath the redwood's visible presence. Redwood trees show variation that develops slowly as each individual responds to the specific conditions it experiences over time. This variation doesn't arise from rapid change or adaptation to extremes. Instead, it reflects how a single biological system expresses itself differently depending on light, moisture, disturbance, and history. Every redwood remains the same kind of tree, yet no two mature individuals are shaped in exactly the same way. One of the most visible forms of variation appears in height varies widely even within a single grove. Some trees rise far above their neighbors, while others remain noticeably shorter despite similar age. These differences often trace back to early access to light. A seedling or sprout that gains a small advantage in height early on may maintain that advantage for centuries. Once a tree reaches above surrounding vegetation, it continues growing in a relatively stable light environment while neighboring trees remain constrained below. Trunk diameter shows similar variation. Some redwoods develop extremely broad bases relative to their height, while others remain more slender. This difference reflects long-term growth patterns instead of age alone. Years of favorable moisture lead to wider annual growth, while years of stress produce narrower additions. Over centuries, these small differences accumulate into trunks with very different proportions and textures. Bark thickness also varies among individuals and along the height of a single tree. Near the base, bark often becomes exceptionally thick, reflecting repeated exposure to fire and physical disturbance. Higher up the trunk, bark may be thinner and less deeply furrowed. Trees that have experienced frequent fire often show thicker bark. The surface pattern of bark carries visible records of variation. Deep furrows, ridges, and scars differ from tree to tree. Fire scars may heal unevenly, leaving permanent asymmetry. Old branch attachments create knots and cavities. None of these features indicate weakness. They reflect the tree's history of interaction with its environment instead of decline. Needle form varies depending on position within the tree. Lower branches, growing in shaded conditions, often carry longer and flatter needles that spread outward to capture diffuse light. Higher branches, exposed to wind and stronger sunlight, tend to support shorter, more compact needles. This variation occurs within a single individual and reflects local conditions instead of genetic difference. Branch structure also differs with exposure. Trees growing at forest edges or near openings often develop broader crowns with more lateral branching. Trees surrounded closely by neighbors grow more vertically, with compact crowns shaped by competition for light. Over time, these differences influence. Root systems show variation shaped by soil depth, texture, and moisture distribution. In areas with deep, loose soil, roots may spread widely and evenly. In rocky or compacted ground, roots navigate around obstacles, creating irregular patterns of support. Interlocking with neighboring trees varies depending on spacing and grove density. Regional variation reflects broader environmental gradients. Redwoods growing closer to the coast receive more frequent fog and experience milder temperature swings. Inland trees encounter less fog and greater seasonal variation. These differences influence growth rate, crown density, and stress levels without altering the tree's fundamental structure. Growth rates vary accordingly. Coastal trees often grow steadily year after year due to consistent moisture input. Inland trees may show stronger variation between wet and dry years. These patterns become visible in growth ring width, and reproductive output varies among individuals. Some trees produce cones more frequently or in greater numbers than others. This variation reflects crown size, light exposure, and internal energy reserves instead of fixed reproductive roles. Cone production may fluctuate over time within the same tree as conditions change. Genetic variation within redwood populations is relatively limited. Long lifespans, vegetative regeneration, and restricted seed dispersal reduce rapid genetic divergence. Despite this, physical variation remains pronounced because environment and history exert strong influence over centuries. Old-growth forests display greater visible variation than younger stands. Differences in height, trunk diameter, and canopy layering accumulate slowly over long periods. In contrast, second-growth forests often appear more uniform. Trees establish around the same time and grow under similar conditions, producing similar sizes and spacing. Variation extends into the canopy itself. Some old trees support complex plant communities high above the ground, including ferns and mosses growing on accumulated organic matter. Other trees lack these features due to branch structure or exposure. These differences arise from form and age instead of species-level traits. Fallen trees also display variation in how they influence the forest. Large fallen trunks persist longer and support more extensive nurse log communities than smaller ones. Their position on slopes or valley floors affects moisture retention and decomposition rate. Each fallen tree shapes recovery differently. Responses to stress vary among individuals. During drought, some trees show noticeable canopy thinning, while others remain relatively unchanged. These differences reflect microclimate, soil moisture, and root access instead of inherent resilience. Over time, such variation prevents uniform response across the forest. That diversity of response contributes to forest stability. When conditions change, not all trees react in the same way at the same time. Some continue growing while others slow. This staggered response reduces the likelihood of widespread failure. Variation in redwoods doesn't result from rapid adaptation. It emerges from long interaction with place. Each tree carries a unique combination of experiences embedded in its structure. Differences accumulate slowly, layer by layer, year after year. The forest becomes a mosaic of individual histories. No two trees share identical timelines. Each reflects a different sequence of light availability, moisture, disturbance, and competition. Together, These differences create a complex but coherent system. Variation doesn't undermine the identity of redwood forests. It reinforces it. The trees remain fundamentally the same, shaped differently by circumstance instead of transformed by it. Over centuries, variation continues to develop. New differences emerge as conditions shift. Old differences remain visible in wood and bark. The forest carries multiple timescales at once, expressed through form. Variation in redwoods is a record of persistence instead of instability. The system remains consistent while allowing individual expression. Growth continues within narrow limits, shaped by environment instead of altered by it. Through this quiet accumulation of difference, redwood forests maintain resilience. Uniformity is avoided not through rapid change, but through long-term interaction with place. Each tree stands as a slightly different outcome of the same enduring process. Redwood trees produce practical outcomes that emerge slowly as a consequence of their continued presence, instead of from any single action or use. These outcomes develop because the trees remain standing for long periods, grow to great size, and interact continuously with air, water, soil, and living organisms. The effects start small and accumulate year after year, becoming noticeable only when viewed across decades. One of the most direct practical outcomes is carbon storage. As a redwood grows, it removes carbon dioxide from the air through photosynthesis and converts it into wood. Each growing season adds a thin layer of new tissue beneath the bark. That tissue contains carbon that was once part of the atmosphere. Because redwoods grow continuously and don't stop adding mass when they reach maturity, this storage increases throughout the life of the tree instead of leveling off early. That process unfolds slowly. In a single year, the added carbon is modest. Over 10 years, the accumulation becomes measurable. Over a century, the amount stored within a single trunk becomes substantial. In old trees that have been growing for many centuries, the total carbon stored in wood, bark, and roots far exceeds that of most other species. This outcome exists only because growth continues, instead of because of any one exceptional year. Carbon storage doesn't end when growth slows or when a tree reaches great age. Old redwoods continue adding new wood, even if the rate of height increase decreases. Each additional layer reinforces the same outcome. As long as the tree remains alive, carbon remains locked within its structure instead of returning to the air. When a redwood eventually falls, the stored carbon is not released quickly. The chemical composition of the wood slows decay. Fallen trunks persist for long periods, sometimes for centuries. During that time, carbon remains held within the wood instead of being rapidly returned to the atmosphere. The practical outcome extends beyond the standing life of the tree. Water regulation is another outcome that develops gradually as forests mature. Redwood canopies intercept rainfall and fog before it reaches the ground. Instead of falling directly onto soil, water collects on needles and branches and then drips downward over extended periods. This spreads water delivery over time instead of concentrating it into short bursts. The effect becomes clearer as trees grow larger. Taller canopies intercept more moisture. Dense foliage slows airflow and reduces evaporation. Over years, soil beneath redwoods remains more consistently moist than soil in open areas. This consistency supports root systems and reduces surface drying. As water reaches the forest floor slowly, erosion is reduced. Soil particles remain in place instead of being washed away during heavy rain. This stabilization doesn't happen immediately. It emerges as roots spread, organic matter accumulates, and fallen wood slows surface flow. Each year adds small improvements to soil structure. Streams near redwood forests reflect this regulation. Shade from tall canopies limits direct sunlight, keeping water temperatures lower than in exposed channels. Cooler water holds more oxygen and remains more stable across seasons. Fish and aquatic organisms benefit from this stability, particularly during warm periods when exposed streams heat rapidly. Soil formation is another practical outcome tied to long-term presence. Needles, bark, and wood fall continuously from redwoods. This material accumulates on the forest floor and decomposes slowly. Nutrients are released gradually instead of all at once. Over decades, soil deepens and becomes rich in organic matter. That slow nutrient release aligns with the steady growth of redwoods. Instead of relying on rapid nutrient uptake, trees draw from a consistent supply. The soil becomes a long-term reservoir instead of a short-term pulse. This outcome can't be separated from time. It depends on uninterrupted accumulation instead of active management. Fallen redwood logs contribute directly to this process. Large trunks that fall remain intact for long periods. They trap moisture, slow water movement, and provide elevated surfaces for new plant growth. Seedlings that establish on these logs experience less competition and more stable moisture than those growing on compacted soil. These nurse logs support regeneration not only of redwoods, but also of other plants. Over time, roots grow down from the log into the soil as the wood slowly decomposes. The fallen tree continues shaping forest structure long after it stops growing. Wildlife habitat emerges as a further practical outcome. As redwoods increase in size, they create vertical layers within the forest. Branches high above the ground provide nesting sites that remain stable for long periods. Cavities form slowly where branches break or decay. These features persist year after year, supporting repeated use. Lower levels of the forest provide shelter in different ways. Root systems create spaces beneath the soil surface. Fallen logs create protected corridors. Thick ground cover maintains humidity. These conditions support mammals, amphibians, and invertebrates that depend on stable environments instead of frequent change. The practical outcome here is not diversity created quickly, but persistence of habitat over time. Because trees remain standing for centuries, the same structures remain available across generations of animals. Habitat doesn't need to be rebuilt repeatedly. Human use represents another practical outcome, shaped by physical properties instead of intention. Redwood wood resists decay and insects. This made it durable for construction when forests were logged. Buildings, bridges, and other structures lasted longer when made from redwood than from many other woods. That outcome had consequences. Large areas of forest were removed to meet demand. The same properties that made redwood useful also made the loss of forests long-lasting. Old-growth stands could not be replaced quickly, and the practical outcome of extraction proved temporary compared to the long-term outcomes of standing forests. In modern contexts, practical outcomes are increasingly tied to preservation. Redwood forests are valued for their role in climate regulation, water protection, and ecological stability instead of material extraction. These outcomes depend on leaving trees intact instead of harvesting them. Recreation is another outcome that develops with time. As forests mature, they provide spaces where people can move beneath tall canopies without altering structure. Trails follow natural contours instead of imposing new forms. The forest offers continuity instead of novelty. Educational outcomes also emerge. Redwood forests serve as reference systems for understanding long-term ecological processes. Their size and age illustrate how small annual changes accumulate into large effects. This understanding can't be gained from short-lived systems. Watershed protection extends the influence of redwoods beyond forest boundaries. By stabilizing soil and regulating water flow, forests support downstream environments. Communities and ecosystems benefit indirectly from processes that occur far upstream and unfold slowly. These outcomes don't appear all at once. They strengthen as forests mature. Young forests provide some benefits, but the full range requires time. Old-growth forests represent an accumulation of outcomes layered over centuries. The practical value of redwoods is inseparable from continuity. When forests remain intact, outcomes reinforce one another. Carbon storage supports climate stability. Climate stability supports moisture patterns. Moisture supports growth. Growth supports further outcomes. None of these effects require acceleration. They require persistence. The redwood doesn't produce its greatest influence through rapid action, but through remaining present year after year. Each season adds a small contribution that can't be replaced by short-term intervention. Where forests are fragmented or disrupted, these outcomes weaken. Where continuity is restored, they slowly rebuild. The pace is measured, and the scale is large. Practical outcomes follow the same rhythm as growth itself. The redwood tree functions as a long-term system instead of a short-term resource. Its presence shapes air, water, soil, and life through sustained interaction. The longer it remains, the stronger these outcomes become, continuing to expand quietly as time moves forward. Redwood trees persist through disturbance by continuing to function while change unfolds around them. Their durability doesn't depend on preventing damage or restoring an earlier state. It develops through layered protection, gradual adjustment, and the ability to keep internal systems operating while external conditions shift over long periods. Fire has long occurred within redwood environments. When fire enters a redwood forest, heat first reaches the outer bark. The bark's thickness absorbs and disperses that heat before it can penetrate to living tissue. Outer layers may darken, crack, or flake away, yet the cambium beneath often remains intact. The tree doesn't lose its ability to move water or produce new wood simply because the surface is altered. During and after a fire, internal processes continue. Water still moves upward from the roots. Surviving needles continue photosynthesis when smoke clears. Growth doesn't restart from a blank state. Instead, new layers of wood are added around altered surfaces while scars remain visible. The tree's structure changes without interrupting its operation. Fire also alters conditions around the tree. Smaller plants and young trees are more vulnerable to heat and are often removed. This reduces competition for light and soil resources. In the years that follow, mature redwoods experience changed surroundings instead of renewed beginnings. Growth continues within a modified environment, shaped by reduced pressure instead of by absence. When fire damage extends deeper into the trunk, the redwood responds by isolating injured areas. Chemical and structural boundaries form around damaged tissue. Decay is confined instead of reversed. Growth proceeds alongside injury instead of replacing it. Over time, the trunk thickens unevenly, redistributing weight away from weakened sections while maintaining stability. Basal sprouting provides another pathway through which durability is expressed. When a trunk is killed by fire, wind, or cutting, the root system may remain alive beneath the soil. Stored energy supports the emergence of new shoots from the base or root crown. These shoots don't need to establish new roots. They rise using an existing network that may be many decades old. Sprouts often grow rapidly at first because resources are already in place. Multiple stems may develop simultaneously, forming clusters that share a common foundation. Over years, differences in light and position influence which stems persist. Some decline while others continue upward. Replacement occurs through gradual selection instead of sudden change. Wind applies continuous mechanical stress, especially in tall canopies. Redwood trunks are built to bend instead of resist movement. When strong winds push against the crown, the trunk flexes along its length. This movement spreads force and reduces the likelihood of snapping. Stress becomes distributed instead of concentrated. Branches may break during severe storms. Loss of branches alters canopy shape and weight distribution. Remaining branches receive increased light and resources. Growth shifts toward these areas over time. The canopy reshapes itself gradually as new growth responds to changed exposure. Root systems contribute directly to this response. Redwood roots spread widely near the soil surface and interlock with those of neighboring trees. When wind loads one trunk, force transfers through shared roots to surrounding trees. Stability emerges from connection instead of isolation. The forest absorbs stress collectively. Flooding and prolonged saturation challenge roots by limiting oxygen in soil. Redwood roots remain concentrated in upper layers where oxygen persists even during wet conditions. Growth slows under saturation, but root systems continue functioning. When water recedes, uptake resumes without requiring replacement of major structures. Drought introduces slower stress. Reduced moisture increases tension within water transport systems. Redwoods respond by easing growth instead of forcing expansion. Energy use shifts toward maintaining existing tissues. This moderation preserves internal balance. When moisture returns, growth continues from systems that remained intact. Fog supports this process during dry periods. Moisture absorbed directly through needles supplements root uptake, particularly in upper canopy levels. This input reduces strain on internal transport, while dry conditions persist. The tree remains hydrated enough to continue operating, even as growth slows. Insects and pathogens act as ongoing sources of damage instead of isolated events. Redwood chemical defenses slow infestation and decay. When insects affect specific areas, damage remains local. The tree isolates affected tissue chemically and structurally. Growth patterns adjust to reinforce unaffected regions, while damaged sections persist. Decay proceeds slowly within redwoods. Fungi colonize deadwood and injured areas, but advance gradually. As decay continues, new wood forms around affected sections. Structural support shifts incrementally. The tree accommodates loss instead of eliminating it, maintaining stability as internal conditions evolve. Durability also appears at the forest scale. Disturbance affects individual trees differently. Some lose branches, others remain largely unchanged. This variation prevents uniform failure. Shared root systems and moderated microclimates support collective persistence during storms and fires. Fallen trees contribute to ongoing function. Large fallen trunks stabilize soil. retain moisture, and slow erosion. They create sheltered conditions that support regeneration. The forest maintains capacity even as structure changes, with fallen wood influencing recovery pathways. Second growth forests show another expression of durability. After extensive disturbance, redwoods regrow faster than many tree species. Canopy cover returns within decades, restoring shade and soil stability. While structural complexity remains limited, core processes resume. Human actions influence durability when they align with these mechanisms, leaving fallen wood in place, protecting soil, and allowing natural fire patterns support existing recovery pathways. Removing structure disrupts continuity and increases vulnerability. Durability in redwoods emerges from the interaction of many traits: thick bark, chemical resistance, regenerative growth, flexible structure, and shared support systems operate together. Each contributes incrementally over time. No single feature ensures persistence on its own. Disturbance becomes embedded in structure. Scars, hollowed sections, and uneven growth remain, while water transport, photosynthesis, and wood formation continue. Change accumulates without stopping core processes. As conditions fluctuate, redwoods continue adjusting growth patterns and redistributing load. Water moves through altered pathways. New wood forms around older structures. Roots expand into available soil while maintaining connections with neighboring trees. And as seasons continue to cycle, growth proceeds alongside disturbance, with adjustments still unfolding in the distribution of weight and support beneath the forest floor. Redwood trees exist within a broader real-world context that extends beyond individual forests and even beyond regional landscapes. Their presence influences, and is influenced by, systems that operate across larger spatial and temporal scales. These connections are not abstract. They involve measurable exchanges of carbon, water, energy, and stability that link redwood forests to wider environmental processes. At a planetary level, redwoods participate in the global carbon cycle. Carbon dioxide moves from the atmosphere into living tissue through photosynthesis. In redwoods, this transfer continues for centuries because growth doesn't stop at maturity. Carbon remains stored in wood, bark, and roots for long periods, instead of cycling rapidly back into the air. Old-growth forests function as long-term carbon reservoirs instead of short-term sinks. That role places redwoods among the most carbon-dense ecosystems on Earth. Per unit of land area, mature redwood forests store more carbon than most other forest types. This density arises not from unusually rapid growth, but from sustained accumulation over long spans of time. Each decade adds to what previous decades have already stored, producing a layered reserve instead of a transient one. Carbon storage in redwoods interacts with broader climate systems. By retaining carbon in biomass, intact forests reduce the amount available to contribute to atmospheric warming. This effect is gradual instead of immediate. It depends on continuity instead of intervention. The longer forests remain intact, the more pronounced their contribution becomes. Redwoods are also connected to regional water cycles. Coastal forests influence how moisture moves from ocean to land and back again. Fog formation along the Pacific coast is shaped by temperature differences between land and sea. When fog drifts inland, redwood canopies intercept it, altering how that moisture is distributed across the landscape. Some water returns to the atmosphere through evaporation. Some reaches soil and groundwater, contributing to longer-term storage. That interaction affects watersheds that extend far beyond forest boundaries. Streams originating in redwood regions supply water to downstream ecosystems and human communities. Because redwood forests moderate runoff and erosion, water entering these systems tends to be cooler, clearer, and more stable than water from deforested areas. The influence persists as water moves downstream, shaping conditions well beyond the forest itself. At a regional scale, redwoods interact with coastal climate patterns. Tall canopies influence air movement near the surface, reducing wind speed and stabilizing humidity. Forest interiors remain cooler during warm periods and warmer during cool nights. These moderated conditions extend outward, influencing local weather patterns instead of remaining confined to forest interiors. Redwoods also occupy a particular place in geological time. Many living individuals began growing long before modern industrial society emerged. Their growth records environmental conditions across centuries, embedding information about rainfall, temperature, and disturbance within their wood. Although these records require careful interpretation, they provide context for understanding long-term environmental change. The continued existence of redwoods connects present conditions to deep history. These trees have persisted through natural climate shifts that unfolded slowly over thousands of years. Their biology reflects adaptation to gradual change instead of rapid fluctuation. This history places limits on how quickly they can respond to new pressures. Human-driven climate change introduces conditions that differ in speed instead of in type. Temperature increases, altered precipitation patterns, and changes in fog frequency occur more rapidly than those experienced in the past. Redwoods respond by adjusting growth rates and canopy condition, but their capacity for adjustment remains tied to slow processes instead of rapid migration or transformation. Because of this, redwoods function as indicators of environmental stability. Changes in growth, canopy health, or moisture stress often reflect broader shifts in regional climate instead of isolated events. Observing these responses provides information about the health of coastal systems more generally. Redwoods also sit within a broader ecological network. Their forests support species that depend on cool, moist environments. When redwood conditions change, these species respond as well. Amphibians, fish, and plants adapted to stable moisture regimes are particularly sensitive. The forest acts as a stabilizing anchor for these communities within a changing landscape. At the same time, redwoods influence how landscapes recover from disturbance. After logging or fire, regrowth in redwood regions proceeds differently than in many other forest types. Rapid early canopy development restores shade and moisture regulation sooner, shaping successional pathways. This affects not only tree composition, but also soil development and water movement. The broader context also includes land use beyond forest boundaries. Development, agriculture, and infrastructure influence redwood environments indirectly through altered watersheds, increased fragmentation, and changes in local climate. Roads and cleared areas modify airflow and moisture patterns, sometimes reducing fog penetration into forested valleys. Protected areas mitigate some of these effects by maintaining large continuous tracts of forest. Connectivity allows ecological processes to operate at appropriate scales. Fragmentation limits these processes by breaking continuity. The broader context includes not just the presence of redwoods, but the spatial arrangement of forests within surrounding landscapes. Redwoods also occupy a place in long-term conservation planning. Because they grow slowly and live long lives, management decisions made today influence conditions centuries into the future. Restoration and protection operate on timelines that extend beyond typical human planning horizons. The forest responds gradually, adding layers of growth instead of reversing change quickly. In this context, redwoods represent systems where prevention matters more than repair. Once lost, old growth characteristics can't be recreated within a single lifetime. Maintaining existing forests preserves accumulated structure instead of attempting to rebuild it later. The broader context extends to cultural awareness as well. Redwood forests have become reference points for understanding scale and time. Their size and age provide tangible examples of processes that exceed human experience. This awareness influences how societies think about long-term environmental responsibility, even when actions remain constrained by shorter cycles. Scientific research also places redwoods within global discussions of forest function. Studies of carbon storage, water regulation, and resilience in redwood systems inform understanding of other long-lived forests worldwide. These insights are grounded in observation instead of theory, drawing on the measurable behavior of trees that have persisted for centuries. As global conditions continue to change, redwoods remain embedded within interacting systems that extend from ocean currents to atmospheric circulation. Their future depends on how these systems evolve and how human activity influences their stability. Responses unfold slowly, with growth and stress becoming visible only over time. Within this broader context, redwoods don't stand apart from the world around them. They are integrated into climate, water, and ecological networks that operate across scales. Their continued presence reflects alignment between biological needs and environmental conditions instead of dominance over them. As seasons continue to cycle, carbon continues to accumulate, moisture continues to move through canopy, soil and growth continues to respond to conditions as they develop, with redwood forests remaining engaged in larger systems that extend well beyond the boundaries of any single grove. Redwood forests present a set of physical conditions that can be observed directly over time without requiring interpretation. Many of these conditions change slowly enough that they are only noticeable when attention remains on the same features across hours, days, or seasons. At ground level, the surface beneath mature redwoods is covered by layers of fallen needles. These needles are narrow and flat, and they fall individually instead of all at once. Some are newly fallen and still flexible. Others are dry and brittle. Over time, additional needles settle on top of older layers, pressing them closer to the soil. When stepped on, the surface compresses slightly and then rebounds, showing that air and moisture remain trapped between layers. Moisture within this needle layer is uneven. Near the top, needles may feel dry during the middle of the day. A few centimeters below, the material remains cool and damp. This difference persists even after several hours without rainfall. When fog has moved through the forest overnight, droplets can still be felt on lower layers long after the upper surface has begun to dry. Small pieces of bark are scattered among the needles. Some are thin and curled, others thicker and fibrous. When rain or fog moisture reaches these pieces, water collects along their edges and underneath them. This creates darker patches in the needle layer that remain damp longer than surrounding areas. Over time, these patches shift as bark fragments move or break down. Trunks show slow, continuous change at the surface. Bark plates expand outward as new layers form beneath them. Cracks between plates widen slightly over years instead of days. Fire scars appear as darkened, recessed areas where the bark surface dips inward. As the tree grows, the edges of these scars move outward, increasing the width of the scar without removing it. During the day, light reaches trunks in narrow bands that move gradually as the sun's position changes. Where light strikes directly, the bark surface warms and dries slightly. When shade returns, moisture from the surrounding air settles back onto the surface. This cycle repeats daily, producing subtle differences in texture and color across the trunk. Higher in the canopy, branches show constant small movements. Even when there's little wind, needles shift as air moves through the forest. This movement is not uniform. Branches on the outer edges of the canopy move more than those closer to the trunk. Inner branches move later, responding to changes transmitted through the structure of the tree. Needles hold water in different ways depending on their position. On exposed branches, droplets form quickly and fall soon after. On shaded branches, droplets remain longer, sometimes merging with others before dropping. This causes water to reach the forest floor in an irregular sequence instead of all at once. Some areas receive moisture earlier, others later. Where water reaches the ground, small darkened spots appear in the needle layer. These spots expand slowly as moisture spreads downward. Adjacent areas may remain lighter in color for longer periods. Over repeated fog events, these patterns recur in similar places, reflecting how branches above direct water movement. Roots near the surface are sometimes visible where soil is thin. These roots are thick and fibrous, extending laterally instead of downward. Over years, they push aside needles and small stones. The surface of the ground shifts slightly as roots expand, changing the shape of small depressions and ridges. Fallen logs show gradual changes along their length. The upper surface may remain firm, while the underside softens where it contacts the soil. Moss appears first in areas that remain damp longest. Later, small plants take hold, where decaying wood meets accumulated soil. These changes occur unevenly, with different sections of the same log supporting different conditions. Water behaves differently along a fallen trunk. Elevated sections dry sooner after rainfall. Lower sections retain moisture. During fog events, droplets collect along the top of the log and then run down its sides. This produces narrow, wet lines at the base that persist after surrounding ground has begun to dry. In areas where streams pass through redwood forests, water movement remains steady after rainfall. Banks show limited disturbance, with roots holding soil in place. The water remains clear, and sediment settles instead of remaining suspended. Temperature changes across the day are small compared to exposed streams nearby. Along stream edges, plants remain close to the waterline. Their leaves remain damp longer due to shade and reduced air movement. Fallen needles collect at the edges, forming thin mats that shift slightly as water levels rise and fall. Animal movement follows established routes. Small paths appear beneath fallen branches and along logs. These paths remain visible over long periods because ground conditions change slowly. Tracks appear in the same areas repeatedly, indicating consistent use instead of temporary passage. Bird activity occurs at multiple heights. Calls originate from different layers of the canopy, often from the same locations across days. Nesting sites remain stable, supported by branches that persist year after year. Growth in redwoods becomes apparent only when compared across long intervals. Annual increases in trunk diameter are thin and difficult to detect without measurement. Height increases are not visible from one season to the next. Over decades, however, reference points such as neighboring trees or fixed landmarks reveal gradual change. Seasonal differences appear without sharp boundaries. Winter moisture increases soil dampness gradually. Spring growth appears as subtle changes in branch tips instead of sudden expansion. Summer dryness is moderated by fog, preventing rapid surface drying. Autumn cooling arrives slowly, altering air temperature without abrupt shifts. Second growth areas show different physical conditions. Canopies are lower, allowing more direct light to reach the ground. Soil dries more quickly. Needle layers are thinner. Growth changes are easier to detect over shorter periods, reflecting earlier stages of forest development. Areas where large trees were removed retain altered conditions. Light reaches the ground more directly. Surface temperatures rise higher during the day. Recovery occurs, but differences remain visible in soil structure and plant distribution. Across all these features, movement and change remain ongoing. Water continues to arrive through fog and rainfall. Needles continue to fall. Bark continues to expand. Roots continue to thicken beneath the surface. Branches continue to shift with air movement, and droplets continue to form and fall from needles as moisture passes through the canopy and onto the forest floor. Redwood forests carry their closing moments through the same physical details that define their beginning. The final stretch of attention stays with what can be observed directly, as conditions continue to unfold without pause. As daylight lowers, light beneath the canopy becomes more diffuse. Bright patches narrow and soften along the forest floor. Trunks hold cooler surfaces where shade settles first. Bark that warmed earlier releases heat slowly, and the temperature difference between sunlit and shaded areas becomes less distinct. Air movement changes as evening approaches. Breezes that passed more freely through upper branches ease. Needles continue to shift, but with smaller motion. Inner branches respond later than outer ones, showing how movement travels through the structure of the tree instead of stopping abruptly. Moisture begins to return to surfaces. As temperatures cool, fine droplets form on needles and branch tips. On shaded limbs, droplets remain suspended for longer periods. Some merge and fall, while others hold in place. Water begins moving downward again, restarting the same paths followed earlier in the day. On the forest floor, the needle layer responds gradually. Areas that dried slightly during daylight regain dampness from above. Darkened patches reappear where droplets land repeatedly. Compression underfoot feels more uniform as moisture redistributes within the layered material. Fallen bark pieces collect water along their edges. Small channels form where droplets travel downward before soaking into lower layers. These channels persist until material shifts again, leaving faint traces of repeated movement. Trunks continue expanding at an imperceptible rate. New wood forms beneath the bark without changing the outward shape in visible ways. Fire scars remain fixed in place, while the edges of those scars slowly widen as growth continues around them. Roots beneath the surface continue thickening. Fine roots absorb moisture from upper soil layers. Larger roots maintain lateral spread, holding soil in place as gravity and water apply steady pressure. These changes don't announce themselves. They remain active regardless of whether they are noticed. Fallen logs continue to change as well. Moisture collects more readily as evening fog develops. Moss surfaces darken slightly. Decomposing wood retains softness, where pressure has already weakened internal fibers. Small plants rooted along the log edges remain upright as water availability increases. Along streams, water temperature cools incrementally. Flow remains steady and banks hold their shape. Roots exposed along edges continue gripping soil, preventing collapse as water levels adjust subtly. Animal movement shifts with changing light. Birds move less frequently between branches. Ground activity concentrates near sheltered areas beneath logs and root flares. Paths remain unchanged, indicating stable use instead of reorganization. As night settles further, fog may thicken in coastal forests. Droplets accumulate more densely on needles and bark. Water movement becomes more regular again, extending moisture delivery across the forest floor without interruption. After sunset, the air cools further. Fine droplets gather more quickly on needles, bark ridges, and branch tips. Some droplets merge and fall in slow, irregular drips. Others run along grooves in the bark before soaking into the needle layer below. Trunks hold their height in the dim light. Roots stay braced in the same shallow spread, holding soil between them. Branches still shift when a small breeze moves through, and needles continue to drop one by one, settling into the layers already on the ground. Later, the drip becomes steadier as fog thickens. Drops land in the same darker patches, then spread outward through the needles. Along the stream edge, water keeps moving at the same pace while the shaded bank stays firm under the roots. Thank you for listening to the Sleepy Mind channel. I hope you have enjoyed spending time learning about redwood trees.